Okay, my time here is already 8 o'clock. We start. So I will run the class for 2 hours. Every 1 hour, after 1 hour, we take a rest, and then we take 5, then we continue on. Okay. Okay. For tonight, our chapter will be magnetic field. Okay. Magnetic field, magnetism. Sorry, magnetism. Magnetism. So this magnetism, we need 2 weeks to teach tonight, and then after that will be next week. Next week, so I see you in the class. That one is the second part of the magnetism. Magnetic field or magnetism is a very difficult subject because it involves something that is like what we call it, quite abstract. Okay, it's very abstract. Oh yeah, before that, if I'm the host of this Google Meet, can you record this one? Because I myself cannot record. If I record, it only look at my face. It cannot look at my that one. Can you record lah? Because I'm also recording at the same time, using other phone, but I'm not sure about the quality of the video later lah. So if you can record, whatever method you just record, because there'll be few group of students cannot come. The reason is because they go to this Camp Bomba. There's one, and then after that they have this caroling. I think they are preparing for the Christmas one. Okay, so that one is we are recording the video for them now. Okay, actually the magnetism one I already have video, but that one is like few years ago one. But it's the same. The way I teach here later, if you compare to the video in my YouTube channel one, it is the same actually. It is the same. Okay, so that's it. Before that, I want to ask, how many experiments have we done? I remember we did Ohm's law, number 1, and then what? Capacitor, right? Ohm's law, capacitor. I think there is one more, potential meter, isn't it? The long, like the ruler one, very long one. 3 only, right? Am I right? 3.
Yes, sir.
So there is another 2. Monday later, we are going to do number 4, which is also using the sliding one, the one that you can slide around. And then after that, after the Christmas week, come back in January, then we are going to do experiment number 5, the last one. That one is a magnetic field related to this chapter. Okay. All right. So we start our chapter 6 now. Okay, this chapter 6 is what we call the magnetism. Okay, magnetism. Now, about magnetism, there are 2 types of magnetism. Okay, one type is a natural magnetism, and then number 2 is man-made magnetism. The one that produced by the Earth or other planets around the solar system, and also the sun itself. The sun has the strongest magnetic field in our solar system. It extends, I think, up to our orbit. Extend up to our orbit, and that one sometimes will interfere with our Earth's magnetic field. But now, nowadays we are not using magnetic field to navigate anymore. We are not using compass anymore because we are using GPS, which rely a lot on this satellite at high orbit or low orbit. Okay, some are extremely low orbit, like 200 kilometer. That one is like a Starlink. Starlink, the one that actually is launched by SpaceX, belong to this guy. What is the name of the guy already? Elon Musk. Okay, Elon Musk. So there'll be thousands of them using this type of GPS using Starlink. But before satellite was launched to the sky, humans use magnetic field, okay, to navigate. And we only know 2 parts of the world, North Pole and the South Pole. And our magnetic field is luckily is quite constant throughout the century. But they actually shift around magnetic field. Earth's magnetic field actually is not really that constant. sometimes the North Pole running up and down for like 10 to 20 kilometer. It's like today it is here, the North Pole, exactly the magnetic North Pole. After that, tomorrow maybe like 20 kilometer away. Okay. So, but after that, it will come back again to roughly the same location. Yeah, that is our Earth's magnetic field. Not really that much changes. But if you're talking about long term, like you're talking about 500,000 years into the future, our North Pole might become the South Pole, and then the South Pole might become the North Pole. So this is what happened. It had been happened for so many times, at least 10 times. Because when scientists study the Earth's soil, magnetification of the soil crystal, they found out that every 750,000 years, our Earth's magnetic field flip. North become south, south become north, right? That one is really a problem to living organism on the surface of the Earth, because that one can cause a lot of problems. Okay. All right. So our Earth. First we look at our Earth's magnetic field. I want to show you the diagram here. This one. Okay. So can see or not? This one here. Of course this one I can see is the Earth lah. This is our Earth. Okay. Now our Earth, if you look at this, this is North America, this is South America, and then the other side, this is Europe, and then the other side here will be Asia, okay, Japan and so on. Now, when Earth has rotate like that, okay, when you rotate like this, now, this is what we call the North Pole. This is called the North geographical pole, and this one here is a South geographical pole. But when you come to magnetic field, at the moment, our magnetic field, the North Pole of the magnetic field is somewhere near the South geological pole. See or magnetic pole, this is a North magnetic pole. Yeah? So our North magnetic pole is at the South geological pole. And then our South magnetic pole of the Earth is at the North geographical pole of the Earth. Right? Why it happened like that? Well, because 750,000 years ago, I think it's about 600,000 years ago, not 700, 600,000 years ago, our North Pole is supposed to be here and South Pole is here. But because of some movement of the Earth's crust and the magma turbulence inside the Earth, our North Pole shift downwards and the South Pole shift upwards. Okay, so you see, it's not yet totally lined up. Okay, this one is not exactly lined. I see this magnetic pole here. This is the geological pole. So this angle here is 23.5 degrees. Okay, this line and this line is 23.5 degrees. You learned that one, right? I think like at least 20 years ago. Okay, 20 years ago. My 40 years ago, 50 40 years ago, 40 years ago, I learned this is what happened. But if you give it another 150,000 years, this angle, the gap will become smaller and smaller, and finally the magnetic pole will line up with our this geographical pole, become one single line. And then after that, it started to shift again, okay, started to shift again for another 750,000 years, and then the South Pole become here, the North Pole will spin to the up. So you see, every 750,000 years, our magnetic pole keep changing. Okay, well, that one happened to the Earth. Now, the Sun happened actually much faster because Sun is a gas. It is a gas giant. So a gas giant movement is much easier. The Sun changed its magnetic north and the south pole every 11 years. Okay, we actually detected that one first. We detected the Sun magnetic field can shift. We call the magnetic field reversal. And for the Sun, it is 11 years. And then planets that have volcano activity or earthquake activity, their magnetic field tends to change as well. Earth is one example. Moon don't have magnetic field because it don't have lava, it don't have magma inside. And then Mercury, we are not very sure because Mercury is bombarded by the sun magnetic field. Venus magnetic field changing all the time. Okay, much faster than the Earth. And then the Mars, very weak magnetic field. So that means it's quite difficult to measure from here. Okay, but we send satellite to orbit around the Mars. Yes, And then Jupiter, Saturn, Uranus, Neptune, these planets are giant gas giant. Okay, they are gas giant. Their magnetic field changes actually much faster compared to the solid planet like Mercury, Venus, and Earth. All right, because we are rocky planet. Okay, we are rocky planet. Okay, so remember this, okay, this one is you have to remember by heart. Okay, question we are not very sure come out or not. Okay, now so that one is the number one. Okay, number one is Earth's magnetic field. Okay, or natural. Okay, natural magnetic field. So natural magnetic field, the one we know is which we are living is the Earth itself. Okay, the Earth itself, and so on. And then this magnetic field. Okay, I will use M field. Yeah, M field stands for magnetic field. M field. Earth's magnetic field, number one, is quite constant. Okay, is quite constant. Now, what is the value of the Earth's magnetic field? Later, you will do in experiment number 5. So it's quite constant. The Earth's magnetic field, we normally use the symbol B. B Earth. Okay, B Earth is a vector, and it is about 5.5 10 to the power negative 5 Tesla. Okay, Tesla is a unit used to measure magnetic field. Okay, Tesla. All right. So this is it strong or not? Well, it can actually deflect high-speed particle from the sun. Okay, deflect high-speed particle from the sun, so it shouldn't be that weak lah. Okay, so we are actually protected by this magnetic field. Okay, but some of the magnetic field still can actually penetrate the magnetic. Some of the particle from the sun can still be able to penetrate because they are so powerful. Kinetic energy are so high, it can penetrate our Earth's magnetic field defense and then hit the Earth's surface. And this is the one that actually caused our DNA to change very, very slowly. Not only our human, I mean living things, it can be plants, animal, plankton, all these things. The DNA change within millions of years, and we call that one evolution. Okay, evolution. So last time they didn't know, they thought evolution is by nature, which we cannot ask a question. But now we know already. Our DNA are actually keep being bombarded by the particle from the sun, okay, especially neutrino and so on. So this particle can actually hit the DNA, and then sometimes it do bad things, like breaking, and then sometimes it do good thing, make it become better. Well, that is all by random, like depend on what is the energy of the particle coming from the sun. Okay, so that is number one. And then number two, okay, Earth's magnetic field has the north magnetic pole at the Earth south geological pole. Okay, geological pole. All right. So magnetic pole, we sometimes use NMP, north magnetic pole, and then the south magnetic pole will be SMP. No? And then this one here will be south geological pole, SGP, south geological pole, if NGP is a north geological pole. All right, just get used to the acronym. Okay, so it has a north pole. Okay, whereas a south magnetic pole at the north geological pole. See, it's all terbalik at the moment that we know now. Okay, it was actually discovered, this change of magnetic field, it was actually discovered by this the ExxonMobil. ExxonMobil is the world's largest petroleum company, of course belong to these Jewish people lah. Okay, so they actually went to this exploration. Okay, everywhere, because oil company, they look for oil. The purpose is everywhere they will go, land, sea. They found out that the crystallized layer, each layer, every 750,000 years, the layer of the crystallized, the magnetic moment actually is always in the opposite direction every 750,000 years. First, they don't know what is actually happening there, but after that, they discovered that one in 16th century, sorry, 17th century. Okay, and then it was only explained at the end of 18th century. Okay, at the end of 18th century, that time is like Einstein, these people become very famous, Nikola Tesla, these people, okay, they explain what is actually happening. The magnetic field reversal theory was actually by Einstein himself. Okay. All right, so there is the Earth's magnetic field. Now, I already show you the magnetic field of the Earth just now. Okay. So from here, okay. So if this is the rotation of the Earth, okay, so we know that Earth rotate at a certain angle, right? Okay, so like this, and then this is the equator. Okay, this is the equator. So if we call this one the azimuth, okay, azimuth means actually the vertical line compared to the solar system. So this one is how our Earth rotate. And this is the one that actually gives rise to the 23.5 degree. Now, our Earth North Pole is here. Okay, this is the North Geological Pole, and this is the Arctic Ocean. Of course, when you say Arctic Ocean, this one is ice because they're damn cold. And then down here, you have a bigger landmass. This one is Antarctic. Okay, Antarctic. Okay, this is a solid land. The ice is about 3 to 4 kilometer thick, very thick ice. Okay, very thick ice. Huh? And then our magnetic field is starting from here. Okay, not really at the line here. This one is the north. Okay, this is the north magnetic pole. Okay, and then opposite to it, this side here, roughly somewhere here, and this one is our south magnetic pole. And again, this one, Antarctic here, this one is the, what we call it, south geological pole. Okay, so this is really what is happening now. Okay, really what is happening now. Yeah. Okay, so the magnetic field coming from the pole, starting from North Pole, okay, and then go up and then become parallel at the equator, and then after that it come down to the South Pole. So the direction of the magnetic field is from north to the south. So it looks like a butterfly actually. Okay, like this. The further it go, the more it extend and so on. Okay, something like this. So how far the magnetic field extended? The magnetic field extend up to 3 times the radius of the Earth at least. So 1, 2, 3. Okay, 3 times from the Earth's surface. 3 times. Another one. So about you have 3 times another 1.5 Earth distance. 1.5 Earth distance from the Earth's surface. Okay, so it's very far. It's very far, and it actually become a protected layer for the Earth itself. Yeah. Okay. So this is roughly what we have in our Earth's magnetic field. This is a natural phenomena which there's nothing much we can do either to change it or what. You cannot do anything on it. It actually fluctuating up and down. Okay. The shape also changes, depends on the activity of the sun. If the sun become very active, our Earth's magnetic field will be disturbed. And that's why you see a lot more of this aurora borealis, northern light, very beautiful light, like turn of light in the sky. It become very active when the sun become active. Okay. So when the sun is very dormant, very quiet, like 5 years ago, very quiet, we seldom can see this aurora borealis. Okay. All right. Now we look at application of this magnetic field. So of course, application magnetic field, natural magnetic field. Application of natural magnetic field. Now, human is the first one to use a magnetic field? Not really. Magnetic field or the compass was actually invented by a lot of civilization, but the one recorded is from China. Okay, actually the Sumerian they have recorded something like this, but they didn't say very clearly whether it is a magnetic field or not. But they said they can use something to navigate. Can you imagine that is about 12,000 years ago? They already know. Okay? China is about 6,000 years ago. 6,000 years ago. Yeah? So that means Sumerian civilization is actually much earlier than China. So of course, because Sumerian, the record are very messy because they use a soil, the stone tablet, and so on. China have written record about 6,000 years ago, but I believe Sumerian is the first one who used, because Sumerian is now, it's Sumerian, right? Sumerian is somewhere around the Iraq, Mesopotamia last time. Is Iraq, Iran, this area, and this area, and that area have a lot of this very olden ancient history that actually, I wonder sometimes, is it because we all starting from there? Okay, all starting from there. So even China also go there and then they look at something and then after that they claim it belong to them. Okay, so well, I'm a Chinese. Sometimes I blame the China also. Because they are not, because China, this country sometimes don't know how to say lah. I hate their people sometimes, but sometimes I like their product. You know why? Because they're very cheap. They're very cheap. They are very innovative. Let's put it that way. Okay. All right. Now, application number 1 by human, of course, is compass. Okay. Compasses is used to actually find your direction. But of course, before you can use a compass, you must have a map first. Okay, your map must be there first. Yeah. So how does this compass work? Okay, so compass have so many variety of compass. There's one here. Don't know where. Somewhere around. Ah, yeah. Oh, don't know where I put. Okay, never mind. Some other time. I can show you next week lah. Yeah, next week in the lab. Okay. Now the compass have this pointer inside. Okay, it has this pointer inside, and normally there is a north. Okay, and then the rest are some other color lah. Okay, some other color. So this is the center, and then here we have scale. Okay, this one is the east, this one is the west, and this one is the south. Only most of the time north is in red color. Okay, and then the arrow here sometimes also have this red color. So now that means if now when you move the compass around, okay, the pointer actually will started to shift around. Okay, the pointer started to shift around. But if the pointer or the arrow pointing at the north, so that means this direction here is the north pole. Now, the north of the compass shows the north geological pole. Yeah, it shows the north geological pole, yeah? not the north magnetic pole. Okay, it shows. That means when your compass point like this, there's a north pole of the Earth. Okay, so that means we know that the north magnetic pole is now here, opposite direction. Why? Because our Earth magnetic field is from the south pole going up, right? So now if you put your compass here, of course the magnet will actually, the magnet inside the pointer, inside a compass, will follow the magnetic field. Okay, why? They are designed to be like this. Okay, this, I draw another one to show you the actual physical thing about the compass. This pointer is made of actually a very small piece of magnet. Okay, a very small piece of magnet. And this part here, okay, this part here is the north pole. Sorry, south pole. This one is a south pole. This one is the north pole. So that means this is a very tiny magnet with a north here and a south here. So now, if you put this compass, okay, on the surface of the Earth, you put it here, the north pole will be attracted to the south pole. Okay, the north pole or the small magnet will attracted to the south pole SMP, and then the south pole of the tiny magnet will be attracted to the north magnetic pole. That's why it points to that direction. So we purposely design this one so that there is an arrow pointing like this and show that, oh, okay, now this north pole of the magnet is attracted to the south pole of the Earth's magnetic field, so that now we are pointing at the north geological pole. All right, so it's simple like that. Okay, so that is the the way how the compass actually works. Okay, but of course sometimes you see there are compass with a lot of numbers, right? A lot of numbers. Well, basically they are still the same. They are still the same. Okay, but modern day compass, right? Like sometimes when you are worried that like in jet fighter last time, right? Even though we have satellite, but sometimes we worry that there's a blackout, something wrong with satellite, and then your aircraft, you don't know where you're going in the dark, especially nighttime. Sometimes when there is a electrical failure on board the aeroplane, then you cannot find your direction. So you still need the basic tools of compass. Those compass are spherical shape. That one is also containing magnet inside. They still have a very magnet, but that magnet is much better than the one we have in the lab. They are much consistent. Okay, so when the magnet is consistent, every time you use the compass, it will always show you the correct direction, unless there are some other disturbance in that surrounding. Okay, but so far, if you're in the sky, there are not much disturbance. If on the Earth's surface near your house might have a lot of disturbance compared to the one in the sky. Okay, so this is by human. Now, how about animal? Does animal use or not? Okay, by animals, yes. Okay, animal also use magnetic field. Okay, so for example, we take these birds. Okay, birds. Okay, now I need a map. Okay, let's say birds. Yeah, migratory birds. Not all type of birds. Yeah. Okay, not all type of birds like chicken. Chicken definitely cannot. Chicken, there's only one direction they go. You know where chicken goes? Any idea? Like Chinese, they like to go to the Great Wall of China, right? And then Muslim, you need to go to this Kaaba, right? Go there. And then a Christian, maybe they like to go to Vatican City and so on. Now, chicken, where do they go? Anyone? Sean, you're the first one enter my this Google Meet. Hello? Anyone? Where does chicken go? Someone try to say something? No idea. Not sure. Sean, not sure. Huh. Okay. Okay, the answer is very simple. You go to KFC actually. Okay, so that is what chicken goes lah. Okay. So Dayang, Dayang. So uh animals, okay, birds especially, migratory birds like flamingos, okay, and then some other those the one that looks like a duck, they fly in a V shape, right? They're in a V shape in the sky, and then a lot of them flying when season come, when your area, not our area, I mean when a certain area is going into winter, winter very cold, difficult to find food, so they will move to area with summer because they had to fly like thousands of kilometers. You're talking about 2 to 4 thousand kilometers, maybe within few 1 or 2 weeks time to reach the destination. So these birds actually they flew, okay, they flew that long distance, okay. But what triggered them? The first one who started that journey, nobody knows what is actually happening. Maybe birds can see differently. Okay, you see, this is what happened to these birds. Let's say we talk about Africa. How does Africa looks like? Okay, so this is Africa. This is the equator line. Okay, equator line. So this is North Africa, and this is South Africa. Okay, and of course, when the South Africa is in winter, the birds need to fly to this direction, okay, to the place where the summer is there. And then after that, another 6 months, then they turn again, 6 months, right? 6 months. After that, they come back here again. So that means like 1 year, they have to fly about two times. Okay, about 2 times. Now, okay, so this one is for migratory. Now, you see here, migratory birds, they only move up and down. Okay, they only know how to move up and then down, like that. They don't migrate from the east to the south. Also from east to the west, west to the south. There's no migration like that. Okay, no such type of migration. Yeah, so migration for birds normally is like perpendicular to the Earth's equator. Now the reason is birds can actually sense the magnetic field, especially when they are parallel. Okay, so they only fly parallel up or parallel down. You can hardly see, some are lost out. Okay, maybe they're lost, right? So how do they sense? Now you have to look at a bird. Okay, this is how my birds look like. Okay, this is bird. Yeah? This is the eyes. Okay, now forgot the wing. Okay, wing. Dia lipat. Senang bertengger ni. Okay. Now, these birds here, we know that when people call you bird brands, that means you're or chicken brand, you are really stupid lah. People call you. Okay, the bird brand is here. Okay, very tiny only, very small. I think smaller than the eye. No lah, slightly bigger than the eyes itself. So this one is a brand. Okay. Now, in front of the brand, somewhere between the eyes and the brand, there is a very tiny pocket of mineral. Okay, and this one is a pocket, something like an organ, a pocket of magnetite mineral. Okay, magnetite mineral. What is magnetite mineral? Magnetite mineral is actually a magnet suspended in liquid, like a jelly type. So the birds actually, not all birds, some birds only, the migratory birds, they have this special organ to actually contain this mineral in a magnetic form, so the magnetic mineral in a jelly form, suspended here. And this one can actually line up with the Earth's magnetic field. Okay, so in other words, the birds can see magnetic field. Okay, they can see magnetic field. Of course, not directly using their eye, they can sense. Okay, they can sense. Just like dogs, okay, they use their nose, okay, to sniff something, and they cannot see it, but they sniff. And then how do they pinpoint it? Okay, when the smell coming from there is stronger, so they follow the direction. After that, they change to the left. That is how they chase down criminal, okay, or maybe looking for a missing person and so on. Okay, cat using their ear. Cat's ear are very sensitive, okay, and so on. These are the ability of the animal, but because why? Because they cannot build weapon and so on. So that is their talent. Okay, that is their talent. So now these birds, they'll fly in sometimes millions of them. Okay, let's say 1 million. Okay, they go there and then they might let's say 3/4, okay, or half of them are female. Okay, so by the time I reach there, it's almost time for them to lay their egg, and then within like few months or maybe few weeks time, the egg will be hatched. Let's say averagely they have this 3 eggs or 2 eggs. So that means by the time I reach there, let's say 1 million here, 1 million, 1 times 10 to the power 6 birds here. Bird. Okay. By the time they reach here, maybe 10% die. 10% die, or okay, 10% die. So now we have 9 times 10 to the power 5 birds. And then at the same time, half of them is producing 2 eggs. And now you have how many already? 1 million plus already. So don't worry about birds is getting reduced. So keep eating chicken. Don't worry about that. Okay. Or keep eating birds in the sky. You see bird, you shoot them down. Okay. They are actually getting more and more. These animal actually, they are more than human. But sometimes when people say that don't kill them, but depends on situation. Okay. Chicken are born to go to KFC. Okay. To go to our dinner plate. if we don't eat them, we can eat some other thing. But some other thing also people will say. And then people say, okay, I'll become a vegetarian. Well, I'm not against vegetarian. If you talk about vegetarian or vegan, for the health benefit, yeah, I believe so. But if you say you want to become vegan because you don't want to kill animal, come on, this is a bullshit, I tell you. You think vegan, what they eat is very holy? I don't think so. You know, you want to plant beans, you want to plant vegetable, you need to have a very good soil, right? Good soil meaning that you have to kill the pests inside there. How are you going to kill the pests when you need to like thousands of hectare? Don't tell me you ask this Indonesian mate come over, go and take the pest. No, no such thing. They use herbicide. Okay, they use herbicide. You kill more than we kill animal actually. Okay, so for those vegan, sorry lah. Okay, this is a fact. Okay, this is a fact. Just that they don't want to admit it. Okay, I don't go against vegan. Okay, sometimes I also like 1 week we take only veggie, but for the health benefit. Okay, don't become a person that your nose are being pulled by someone. Okay, make up your mind. Okay? Make up your mind. Think wisely. Don't just follow or TikTok say this or I believe, and then this YouTube say this I believe. Okay, so go because you are a science student, so you should be able to analyze. Okay, now so this is what happened. So the birds migratory, they use magnetic field. So that's why when they fly, they can fly continuously 1 week to 2 weeks time, continuously non-stop, and non-stop. But of course, some die in the middle of the flight because they got heart attack. Ada yang patah sayap, right? Patah pak, ada yang mid-air collision. Okay, ada yang kena bunuh sebab dia ambil girlfriend orang lain. A lot lah. And then some kena lightning sebab dia derhaka kepada Tuhan and so on, right? Not sure they got religion or not. No, we're not very sure. Okay, so this is in birds. Okay, in birds. Yeah. Now, another a more interesting, not story. It was actually a study by the National Geographic team. It's a 20-year study. Okay, the second one is the turtle. You know turtle, right? Turtle, when they are born, okay, they hatch, of course, from the egg, turtle egg, and then the first thing they do is what? What's the first thing they do? First thing they do is they crawl themselves, pull themselves out from the sand, beach, okay, beaches, from the sand, and then the first thing they run to the sea. And then, of course, not many will be successful. Okay, not many will be successful. Why? Because there are animals tend to eat them. Okay, tend to eat them. This animal, including human, human also eat them when they are in an island when there's no camera looking at you. Nobody pause and complain about you. You eat. Okay, so this turtle when they are still small, they rush to the sea. Maybe like hundreds of them, maybe thousands of them. Okay, so they rush to the sea, and then some might lost. Instead going to the sea, they go the opposite direction. These are the lonely type. Okay, they go to the jungle, and of course, jungle is not their habitat. Sure, they will die one. Okay, so they're in the jungle. They're even more problem. Okay, now the one that reach the sea, when they step into the sea, swim in the sea, there will be fish waiting for them already. Okay, fish waiting for them. So for the first year of their life, first 6 months at least of their life, they are only very near. If there is a coral reef, okay, coral reef, they can hide around in the coral reef, hide under the plastic bag, hide under the seaweed and so on, okay, and so forth. So this is what they are doing for the first 6 months until their body mass increase to about 1 kilogram, roughly like 1 kilogram. Okay, so after like 1 year, like half a year to 1 year, they increase body mass to 1 kilogram. Now, when with the body mass of 1 kilogram, they can venture into deepest part of the ocean, but it's still like within 1 or 2 kilometer only. Okay, 1 or 2 kilometer only. So they need to wait for until few more years until their body weight go up to at least 5 to 10 kilogram. 10 kilogram is very common. And then they started to venture into deep ocean. Okay. Now, what they realize is, I will draw a map here. This is our Malaysia map. Okay, what I want to show you is this. Okay, this is Sarawak, Sabah. This is I'm talking about Terengganu here. You know Terengganu, there's one place called Rantau Abang, right? Rantau Abang is the world's most famous place for turtle to land, okay, to lay egg, okay, and there'll be a lot of tiny turtle hatch every turtle season, okay, every season. So now when the egg hatch and then after a few years, so now this big turtle, okay, this big turtle, especially the female one, okay, you know the female, right? I'm talking about the female. Huh? Of course, the male one also have lah. The female one have one mission only. This is a female, is it? This is a female. Now, this female have only one mission. Okay, what are their mission? Okay, let's start the story. Now, we know that Sabah is here, and this is a Philippine, this area, right? Philippine. Okay. So after that, we have what? The world largest island, 4,000 kilometer away. This is Australia. Okay, Australia, and then we have this this area. The outside of Queensland, this area here is an area with the world richest coral reef. Richest coral reef. You can find almost any type of fish in this region. You got small plankton, you got small plankton, you got small fish, you got small fish, you got medium fish, you got medium fish, you got big fish, you got big fish, you got sharks, jaws, and so on. And any other type of living creature we will say here, because this is where the place, the hot water from the equator meet the cold water from the Antarctic. And it make a moderate zone. This moderate zone is something like what we call it, the Great Wall of China to the Chinese, the Kaaba to the Muslim, and the Vatican City for the Christian. See not? So this is a place where most of the living thing, if they are able, they try to come here for two reasons. Okay, number one is to find food. Okay, of course, this is a very luxury place. So now this female turtle, okay, female turtle, when they are caught by this National Geographic scientific team, they actually tag them, put a GPS on them, and you try to check them. Not only one, I think they tag thousands of them from other places also, but we're talking about the one in Malaysia. So this female turtle, we will call it, her name is Mary. Her name is Mary. Well, actually, Mary is the name of the person I hate the most in my class last time when I'm in secondary school. Just to let you know, that's why I call Mary. Okay. Now this Mary here, which is a turtle, is going to go from here, swim, of course, whatever style, okay, butterfly, whatever, and then he might stop here to find food, and then tell his cousin that he's going to go to the Kaaba there or the Vatican City here, and then he's going to swim. Of course, there are islands around, there are islands around here and there, very remote island, and then some they might go here, go there, and then this is like their station, okay, their station, outpost station, go there, and then finally they will reach here. All right, now what they do here, not only to eat, right? Okay, not only to eat, but they also want to enjoy life. Okay, if there are female turtle here, if we have a female turtle, we also have this male turtle, isn't it? The arrow just fit into here, right? So now they will have like party around, okay, having a dancing party and so on, and then they fall in love and so on, and then the next few days, this female turtle go to the pharmacy to check on their pregnancy, to buy pregnancy kit, and then they realize that, oh shit, I'm pregnant. Okay, so this one is pregnant, maybe this one also pregnant. So when the turtle got pregnant, they had this very instinct. The first instinct is go back to where they came from. So now the journey is going in the other direction now. So instead of coming down from, you cannot see the orange color, right? Okay, this is where it comes from. Yeah, right? Now you can see. After that, it's going to go back to almost the same path, and then go back to exactly the same location, about few meters away from where where she was born, to lay the egg. By the time it reach here, there is almost like half a year already. Okay, the egg is already enough, okay, to be like laid on the into the sand. Okay, so this is the turtle story. Okay, now the question is, how does turtle can actually trace back? You don't see turtle wear the watch, the GPS watch, dia tak bawa handphone pun. Okay, dia tak belajar pun, fizik pun dia tak tahu. Okay, but they had a talent like a bird, except they have a better resolution. Okay, uncertainty is much better for the turtle because their brain are much bigger, and then the ability to detect the magnetic field, and also the second one is the Earth's gravitational field. They can detect that when that two field are being calculated by them. How they calculate, don't ask me. I never been a turtle before. Okay, so they can actually diagnose that two field, and then they pinpoint the direction in reverse. Now just now they come here, right, and now go back in reverse. That is how they are traced by this satellite. Okay, but of course not exactly on the same path lah. Okay, some of course will get lost, the one that malfunction, no? Okay, malfunction, and then yang tak bayar bill, okay, they pun lost to somewhere here and there and so on. Okay, so by the time they reach here, they lay their egg. After that, the same process happen again. They're gonna go there again. So their whole life is repeating. Okay, for the purpose of mating, for the purpose of the next generation. Okay, so that is how it works. So next time, if you want to go to Miri, Bintulu, or Sabah and so on from Kuching, right, or Samarahan, you just put a turtle on your car. Yeah, turtle, just whisper, yeah, I want to go to Miri. You use a flipper, left, right, tell you. You don't even have to pay your handphone anything, isn't it? Okay, so it's a much better solution if you can't afford. But the problem is, where are you going to get the turtle? Okay, put on your car, right? That is a very good question. All right, so these are the where the animal actually use the magnetic field to navigate. Okay, all right, so that is our application. Okay, the application for magnetic field. Right. Okay, any question? Can we proceed? Okay, so we proceed. Minum dulu. Okay, the next one now, our natural magnetic field already finished already. You open the file. Okay, so that is the magnetic field, natural and non, the one that is produced by human. Yeah. Now we look at the one, first one just now. This one is natural magnetic field. Now we go to the man-made magnetic field. Okay, man-made magnetic field number 2. Okay, man-made magnetic field. Well, of course, the story of the discovery of the magnet is actually from, the shepherd, the shepherd who take care of sheep. So what happened is one day, this shepherd, okay, the shepherd actually, okay, this is the shepherd. Okay, this is the shepherd, right? This shepherd is taking care of a lot of sheep. Now, he actually have to use stick, okay, use stick, okay. You have to use a stick to actually, what we call it, to like, okay, knock at the stone to actually chase the sheep from one location to another location, okay, because sheep are like, well, You know, they are not very intelligent. Okay, so we have to produce sound to scare them. Okay, so that they will move to one of the direction. Okay, to one of the direction. Yeah. All right. Now, every few months, because the stick is used to like hit on the stone, so it got broken. Okay, it got broken or fiberized. Okay, fiberized, I mean they have to change a new one. And you know, in the places where sheep is a lot, we only have a lot of grass. We don't have tall tree so you can produce a lot of stick. So to get stick is very difficult. So what they did is they actually cover the whole stick with iron. Okay. Now the whole stick now, the lower part is covered by iron. Yeah, they have iron last time. Of course, they have iron. So now when you use that, okay, use the same stick covered with iron to hit at the stone, you are producing a stronger sound, higher pitch, and the stick lasts longer. Definitely longer as long as the iron is used to cover the stick. But in one particular story, well, this is just a story. We are not very sure about that. One of the shepherds actually go to another area or grazing ground for the sheep. So there's one time he knocked at the stone using the stick covered with iron. And the stick was actually attracted to the stone and it's a bit difficult to put it away. And then for this guy, of course, it is considered something very magical because you know that last time this is like 12th century, maybe just 1 century at that time, 2 century, 200 century. Okay, so at that time, magnet is not something that is very familiar to them. For us, it's very familiar. Okay, it's just normal thing. Everywhere you can see magnet. For them, it's something very magical, very wizard. Okay, wizard or maybe witch and so on. So they actually call that piece of stone magnetite. Why? Because the village is called Magnetite village. Okay, Magnetite village. It's a very special Viking name. I'm not very sure about that, the story also. Uh, but I also suspect whether the story is real or not real. Okay. Now, this is the discovery of the magnet recorded by I think one of the historical book in Europe. Okay, in Europe, right? In Europe. So now, of course, China, Jiasu type. They say 5,000 years ago they already discovered magnetic field. First magnetic field, but they didn't say magnet. They didn't say magnet. Yeah? So now that is the first discovery. So from then on, they started to use a stone to do a lot of other things, keeping their metal together, metal chunk together, especially the blacksmith. They are going to use it to keep things together so that they don't lose it. Okay, and then they started to make money using iron. Okay, using iron so that using iron, of course, for normal people, but if you are higher ranking, you don't use iron, you use gold and silver. Iron is for like people that is very low, okay, very low level. Long time ago, they have like have a what we call casta one, okay, not ours. Now, what happened next is humans started to evolve in using that actually magnetic property. Okay, so the magnet, the first one made by human in quite a modern day will be bar magnet. Okay, bar magnet. I mean, the first type. Okay, the first type is what we call that. Hmm, bar magnet. Okay, so bar magnets looks like this. Okay, one side is north, another side is south. Okay, and also you have another type is called the rod magnet. Rod magnet. Okay. Rod magnet, of course, something looks like this. Okay. And one side, of course, is north, another side is south. Okay. So these are the rod type and the bar type. Of course, the magnetic field pattern are the same. I think I have the magnetic field pattern. Okay. Something like this. Okay. So this is the magnetic field pattern that we can see. Okay. The north, okay, magnetic field come up from the north and then go into the south. Okay. So this one is our magnetic field pattern. Oh, no more. Only the one. Okay. All right. So that is the one that made by them, but of course not as shiny as the one we can see today. They are quite crude. Okay. Quite crude design. Yeah. Okay. So this one is the one made by human, and then of course when time evolved, okay, they design U magnet, U shape. Okay, U shape magnet. Okay, U shape magnet of course looks like this. Okay, and then after that we have horseshoe magnet. Okay, horseshoe shape. Horseshoe is a U, but except they are like being bent in. Okay, bent in like this. Like that. The purpose is to produce a very intense magnetic field. The difference, yeah? This one not really that intense, but this one is actually much stronger because they are nearer to each other. Okay, the field here is stronger compared to this, north to south, north to south. So the nearer you bring it, the more it can actually the force is stronger in attracting object. Okay, so these are the one actually built, manufactured or shaped by human. Okay, now the material used to make magnet. Okay, material used. Yeah? So material is cobalt. Okay, and then number two, cobalt you need nickel. Okay, and then you need some other thing like chromium. Okay, it depends. If your magnet is not the shiny type, it's the black color matte type, it don't have chromium. But if your magnet is silver type, you have chromium inside. Okay, and of course some other rare earth material like yttrium and so on. These are the modern day of making magnet. Last time actually it's quite the same. Okay, quite the same. Yeah. So magnet like this is called permanent magnet. Okay, we call this one permanent magnet. You cannot switch them off. Okay, it's always there. If this magnet is very strong, if there is an object attached to it, sometimes it's impossible to take them away. Okay, so now there's one way to actually make the magnetic field weaker. You heat them up. Okay, you heat the magnet, you make the atom become random inside. So when the atom become random inside, it weakens the magnetic field. Okay, it will weaken the magnetic field. Yeah. Okay, so that is the one we call permanent. No? So these are all permanent magnet. Okay, so permanent magnets cannot be switched off. Okay, that is a problem. If it cannot be switched off, the usage is actually quite limited. Okay, quite limited. You cannot use it in a relay. You cannot use it in an earphone. You cannot use it in whatever things that you need to switch on and off at high speed and so on, for example. Okay, so people started to think, how can we produce magnet that can be switched on and off? And that era come when they invented the electromagnet. Okay, electromagnet. Okay. Okay, we take a rest, so we take 5 minutes and then you come back again after 5 minutes. Okay, now it's already 9 o'clock. So come back at 9 okay lah, 10 minutes. Then 9:10. You come back at 9:10, yeah? Hello, welcome back. Welcome back. Okay, we continue. The next one, just now we are talking about permanent magnet and also electromagnet. I think I have electromagnet here. Let me check that. Oh, sorry, don't have that. 没有. Okay, so this electromagnet, of course, discovered by this what we call that Michael Faraday. Michael Faraday. That's why in Form 4, Form 5, you learn something called Fleming left-hand rule and Fleming right-hand rule, right? That is the important thing about the rules. Now, of course, when we talk about magnetic field that we can control, the only way to control magnetic field is through current, okay, electric current. Yeah. Okay. First, we look at before we look at type of magnetic field produced, okay, by current. First, we look at how are we going to use Fleming left-hand rule. Yeah. So the next thing that we're going to look at is number C. Should be C, right? Sorry, B. The one B we call the electromagnet. Okay, electromagnet. So electromagnet, from the words you can see that magnet is a magnetic field, and then electro is electrical system. So electricity produce magnet. Okay, electricity to produce magnet. Yeah. So now, of course, basically we have this. One of the basic electromagnet is you have this iron. Okay, iron, and then you put wire around the iron. Okay, like this, and then you connect it to a battery, and what happens is when you close it, this one will become magnet. Okay, here will become north, the other side will become south. All right, so that is what happened in electromagnet. Of course, this one is the world's most important discovery. It is used in almost anything that move. Electric motor actually, or motor. Okay, electric motor is actually basically function based on this, whether it is AC, DC, or brushless. Okay, or brushless. Like for example, the drone nowadays they're using brushless. They can spin faster, so it's more consistent torque and more powerful, and you don't have spark. Okay, that one is all based on electromagnet. Okay, all based on electromagnet. Yeah? All right, so from here, you can actually change the shape into something else. For example, you can actually make it into a U shape. Okay, it can be a U shape like this. And then, of course, you can put the wire around here so that if the current go in here, so this one will become the North Pole. This is the South Pole. This one is even more powerful than this one because when you try to attract something like this, there are two poles trying to actually attract it. This one, if you pull something, there's only one pole. Okay, so this side wasted. Okay, this side wasted. So that's why people invented like this. And if you want to make it even stronger, remember, you just make them closer so that they are in the shape of a horseshoe shape electromagnet. Okay, so these are the man-made. Okay, man-made, but the one that we can control. If you reduce the current, magnetic field become weaker. You increase the current, magnetic field becomes stronger. Okay, that's it. Simple. You control current, you control magnetic field. Okay. All right. So next one. So these are the basic thing about type of magnet, yeah, permanent and electromagnet. Okay, the next one they're going to see will be C. Okay. Well, sorry, this one is the next part already. We call this one the magnetic force. Okay, magnetic force, and this one is actually under Fleming left hand rule. Okay, short form Fleming left hand rule. Okay, in exam you can in your test 2 later you can use a short form Fleming left hand rule. Okay, it's understood. Fleming right hand rule will be Fleming right hand rule will be FRHR. Okay, so that one is understood lah. Okay, understood. All right, now magnetic force, when we look at this if we are talking about Fleming left hand rule first, yeah. Okay, so I'm going to draw something like this. This is the middle finger, sorry, index finger, this is the middle finger. Okay, This is my, okay, this is my hand. Okay, now they are all 90 degree. Okay, they're all 90 degrees each other. Yeah? Now this one I will label it as F. This one I label as B. It's very easy to remember. I, FBI. You think you watch this Hollywood movie, always got CIA, FBI, right? Very easy to remember. FBI. FBI. Same thing if you are using your right hand rule. Okay, they are mirror image. So now in this case is FBI. Okay. Now F stand for what? First we look at what are they stand for. F is magnetic force. Okay, magnetic force. And then in Newton. Okay. And then number 2, B. This one is magnetic field in a unit of Tesla. Okay. And then I is the electric current. Of course, in ampere. Okay, in ampere. All right, so that one is the FBI, what it stands for, and they are always 90 degree. We call them perpendicular to each other or orthogonal. Okay, orthogonal, perpendicular to each other. Now let's find out how are we going to use this method, our Fleming left hand rules, to direction of the force. Okay, and of course there will be formula as well, and there will be formula as well later. How are we going to calculate the magnitude? First, we want to know direction only. Okay, example 1. Okay, example 1. Now let's say you have 2 magnets. Okay, and let's say this is the north, this is the south. Okay, and then there's a conductor here. Okay, there's a conductor carry current. Okay, in this direction. Okay, I use color to represent the current. So current, I use purple color. So this is the direction of the current. I. Okay, I. Current flow from this conductor from P to Q. Okay, current flow from P to Q. And then magnetic field, I use red color. Okay, so magnetic field, I use green color. Okay, I use green color. Magnetic field normally is from north to the south. Okay, north to the south. Yeah. So in this direction, so this one is the B. Okay, the B magnetic field. So now we want to find the direction of the force. How will the conductor move? Is it moving up or down? Is it moving to the left or to the right, or moving towards Q or towards P? So we are using this one. Okay. So we know that this is FBI. So maybe in an exam you can write something here, FBI tiny so that Mr. Robin and Sir Freaky cannot see. Right? Okay, now first we point it to the direction of the magnetic field because we want to find F. So we point our finger to the B first. This is a B field, so we follow like this, Okay. So now my finger is now in the same direction as the green vector, like this. And then after that, you have to make sure that the current also follow the I direction. So I make sure that this one stay the same. The only way to do it is like this. Okay. So you can see that my middle finger is pointing to the I direction. My index finger pointing to the green color vector, which is a magnetic field. My thumb point downwards. You try that. Okay, you try that. So that means this conductor is going to move downwards. Like that. Okay. So that is how we're going to use our Fleming left-hand rule to find out the direction of the force. All right. Okay. Another example here. Orang main metun. What day is that? Okay. Now I don't want to draw magnet anymore. I'm going to use, okay, arrow to represent. Now my magnetic field is there is a conductor. Okay, conductor carry current. Okay, carry current in this direction. This is the I, and then my magnetic field enter the paper. B in. That means the magnetic field is entering my paper here. So find the force on the conductor. Okay. So again, we always start with the magnetic field here. So point in. Okay, point in. You cannot see here, right? Point in. Everything three-dimensional. Never mind. Point in, and then if I move, see, my index finger pointing in, and then my middle finger actually point to the right hand side, current. So my thumb actually point upward. Okay, upward. So you can see that this is the direction of the force on the conductor. And it is a vector. Don't forget, vector, vector, current also vector. Everything are vector. Everything are vector. Okay, another one. B. Now my magnetic field is, let's say, pointing downwards. Okay, and then the conductor carry current to the current. I use what color? Purple, right? Okay, so this one is a current, and then this one is a magnetic field downward. So now find the force. Same thing. This one is still 90 degrees with each other. Okay, first point to the magnetic field downwards. Okay, a bit difficult for you to see. I should have bought a very small, tiny hand. Okay, like this, and then I have to point to that direction. See, right? So magnetic field downwards, current to your right hand side, my thumb into the paper. So how do I draw the force like that? I draw a circle, a cross, and then put an F here. Okay. A circle with a cross, meaning it looks like arrow flying away from you. So the force is into the paper. Okay, into the paper. So that is example number 2B. Right? Well, of course, this one, of course, not yet involve calculation. Okay, no calculation involved. So now we're going to look at what is a formula. Okay, what is a formula if you are asked to calculate the strength of the magnetic field? Yes. Okay, come to page number 6. Okay, so let's look at this diagram. We assume that there is a magnetic field, okay, pointing to the right hand side. Okay, so this is magnetic field B. Okay, magnetic field B. And then there is a conductor. Okay, we put a conductor inside the magnetic field. The whole conductor must be inside the magnetic field. And then this conductor carry current from P to Q. Okay, in this direction. And this one is a current I. Okay, and the current direction of the conductor itself is making an angle theta with a magnetic field B. Okay, yeah, the current I, okay, is making in that direction of the PQ rod conductor PQ is making angle theta with B. So the direction is current from P to Q, magnetic field to the right hand side, and then the length is L. Okay, the length is L. Okay, now this length here is always pointing from where the current enter and where it come out. So current enter from here. So P is the initial point. And then Q is where the current come out. So this one is the final point. So when current start from here, end up here, it has a displacement L. Okay, displacement L from P to Q. Yeah. So now, knowing the L value, knowing the theta, knowing the B, knowing the I, we can calculate the force acting on this rod PQ. Okay, so the formula on the force is this one. The magnetic force on conductor PQ is given by this formula. Okay, F is equal to I L cross B. You already learned cross product, right? Okay, you already learned cross product in your physics one what you call that, 110, isn't it? Okay, physics 110. Okay, so this formula, if it is a cross product, then we can actually calculate the magnitude of the force, which is I, this one is LB, cross product is sine theta. Okay, LB sine theta. Or we can simplify them as F, and this one become ILB sine theta. All right, so that is a magnitude. Okay, magnitude of the magnetic force. All right, equation number 2. Okay, so formula will not be given in exam. So same like your test one. Next week I pass back the test one to you already. I mark. Still got a few students fail. Some even got 3 marks only. I'm going to personally strangle you in the class later when I pass it back to you. Okay. Some can get 29 marks over 30. So it's not the question's problem. If you look at the question actually quite similar to your tutorial, unless you're not doing your tutorial. Okay. So later next week when I give it a tutorial, the exam paper, you will know. Okay. But I still need the paper to be second mark by Dr. Ahmad Lutfi. We need a second mark to check. Okay. So we look at example how I'm going to use this equation. Okay. So remember all the value, okay, use, okay, I mean all the unit. The force will be in Newton, your current will be in ampere, magnetic field in Tesla, the length will be in meter, and then also the angle will be in degree. Okay, in degree. Okay, now we look at example. This is example number 3 already. Okay, example 3. So example 3, let's say we have this magnetic field. Okay, B is 2.50 10 to the power, let's say we need it to be very small. We want it to be very small. Let's say -6 Tesla. It's actually like oh sorry, not this value. We normally give in prefixes. So it is 250 micro Tesla. 250 micro Tesla. You know micro, right? 10 to the power -6. Okay. And then there's a conductor. Okay. PQ. Okay. The length of conductor PQ is 80 centimeter. Okay? 80 centimeter. And then it carry a current I. Okay. Carry a current I. The current is, let's say, 15.5 ampere. Okay. And then the angle theta here is 60.0 degree. Okay. So the question is very straightforward, very simple. Find the magnetic force on PQ. Okay. Find the magnetic force on PQ. Okay. When you are asked to find magnetic force, remember you need to give 2 things. because force is a vector quantity. Number one, you have to give the magnitude, calculate based on equation 1 or 2, and then you need to give direction of the force. Direction, in, out, up, down, left, right, and so on. Okay. So first we calculate the magnitude of the force. We already list down things that is already here. Okay. So now we write down the formula. F is equal to ILB sine theta. Okay. Sine theta. So our force magnitude is current 15.5. Magnitude, length 80 cm, 0.800 meter. Everything must be SI. Sometimes you forget. Okay, sometimes you forget. And then the magnetic field is 250 micro Tesla, 10 to the power negative 6. And then sine 60 degree. Okay, sine 60 degree. So that one, we need to use calculator to get our answer. Yeah. Okay, so first one 15.5 multiply 0.8 multiply 250 negative 6. Okay, you got this, and then multiply by our answer here, multiply by sine 60. All right, so that is our answer. 2.68 10 to the power negative 3 Newton. Okay, it's a very small force, but detectable. Okay, we can detect them. Detectable. Yeah? Okay, there is a force. Now come to the direction. Now, how are we going to use the direction? Fleming left-hand rule. Okay. Our Fleming left-hand rule normally is 90 degree, right? 90 degree, but you can actually the angle is between the current and the magnetic field B and I. The angle between them 60 degree, right? So in our case here, you see, first we point to the magnetic field. Okay, so our magnetic field is to the right hand side. Okay, to the right hand side here, and then your current. This is a current, FBI current. So current go up to the flip like this. See or not? So no matter what angle here, 90 degree, as long as they flip like that, your magnetic the force is into the paper. Right? You can try it. Yeah, you can try it. So I draw like this. Here first. F. Alright. So you can write down here also. Other than this, if you can draw like this, I give you mark. If you write here also, I give you mark. Okay. The force on the rod PQ is into the paper. Okay, into the paper. All right. So that is our example for this what we call that magnetic force. Okay, magnetic force. Okay. We go for another example. Okay, example 4. Okay, example 4 now. What to give you? Example 4. About the same thing, except now my magnetic field is into the paper. Okay. Okay, this is a region. This is a place where the magnetic field exists. Okay. B, C, D. Magnetic field enter the paper like this. And the B in is equal to 355 millitesla. Okay, 355 millitesla. This length here is 80.0 centimeter. This side here is 90.0 centimeter. And there is a rod, a conductor, PQ, okay, PQ, which carry a current I. Okay, the current I is 20.5 ampere, and the length PQ, Yeah, the length PQ is 2.50 meter or 250. Okay, 250 centimeters. Okay, 250 centimeter, easier. Okay, so now the question is find the magnetic force on PQ. All right, find the magnetic force on PQ. All right. All right, so now I give you 5 minutes to calculate the force. Okay, starting from now. Okay, give a time. 5 minutes.